So let's just bear with me. We're just going to try to do the best we can. So this is presumably about twice of ME, and then this is ME. So we're going to try to find out what is ME. And one can start by starting with the idea of physical volume again of a chain. And that physical volume should be proportional to chain length. And therefore, why not? It is simply R squared, because R squared is proportional to chain length. Okay? And then, of course, on this side, you have volume. On this side, you have length. So there is a missing length. So we don't know what it is, but we know it's a missing length. And this concept has nothing to do with the packing model. This concept simply exists because we realize the physical chain is linear in chain length, and this must be true. I have physical volume on one side, which is nothing but the reciprocal of the number of chains per unit volume. In other words, this is the number of chains per unit volume, which means in each volume there will be one chain. So this concept we have introduced before. The number of moles per unit volume, each mole has this number, Avogadro number of chain of molecules. So this is the number, see, the number of chains in your total system and the total volume. Therefore, the reciprocal of that is, of course, what each chain occupies. And that goes back to the physical volume. So this is true. So there are really two parts. The packing model involves this packing length. The real important thing is to figure out ME. How do we figure out ME? Well, we know you got a chain that's, as I depicted, it will have a volume, so-called pervaded volume. So there are two concepts, right? One is physical volume, the other one is pervaded volume. This pervaded volume, of course, is something like 4 pi over 3 r cubed. In fact, if you're careful, you say radius of gyration cubed. So that's the pervaded volume. And you know this space is open, so there are, oh Lord, because of my mismatch. In this volume, there are other chains. I'm not going to draw all of them that fill the same space. And two things that test, well, at least one thing that tests your intuition. First is, as my chain length increases, this volume increases because this goes as n to the 3 halves, right? Because R is n square root of n. Okay? So, over to here. So, it's clear when I double my chain length, when I double my molecular weight, my volume will increase by what? Exactly 2 when I double it, 2 times square root of 2, which is 1.4, so it's about 2.8. So each time I double it, I tripled my volume, roughly speaking. Which, of course, means as my volume increase, there will be more chance that can come into my own space. Yeah? That concept is clear. So the point is, pretty soon, it's too clouded, meaning I see too many of the same chain, the same length in my own space. And so let's figure out that concept directly. And which means we're going to find out how many chains are there in my space. Right? Do you see how slow the computer is? I changed the color and then it didn't change it. It's actually stuck there. So that's easy because we know the pervaded volume. Which is open. And we also know the physical volume. Which is what this chain, if it collapses, would occupy. Yeah? And of course, this open volume can accommodate many of these collapsed chains. And that's what it is. This ratio will tell you how many chains are there. Right? And how many? Well, you know roughly. It's 4 pi r cubed divided by 3. I'm going to eventually even ignore the prefactor, so-called. And this one, you know, this is where I'm happy to indicate the packing parameter, P again. But essentially, it's PR squared, if you recall. It's still here, if your eyes are. It's on the slide number 40. Right? That's it. And what this leads to? It leads to something very simple. It's basically R over P. Yeah? Oh my God, how simple can this be? It's R over P. And the packing model is all about having this. Can you believe this computer? Right now it matches, and then in a little bit it will be off calibrated, and then come back. Who can solve this problem? You see, right now it's precisely calibrated. Okay, so in any case, the whole idea of the packing model is this conjecture. Very bold conjecture. And it turns out to work. I once even figured out that conjecture myself, but only to realize they have proposed it for a long time. Which means what? Which means it's reasonable. Which means if you put your mind on it, you would have guessed it. And the conjecture is what? That, remember, I'm going to do it freely. Your molecular weight is nothing but your chain length. So these are one-to-one. Huh? Always one-to-one related. So, in fact, for ME, I can even say there is such thing called NE. They are just the same thing proportion. So what we're saying? We're saying at the onset of entanglement, okay, at the onset of entanglement is a point, when we say onset, we mean this. You have a short chain, you keep making this longer, you keep making this longer. There will be a moment when the chain is as long as an E, such that in its own pervaded volume. In its own pervaded volume, there are enough chains. In other words, there are so many chains that it's too crowded. So let me go back one step. Look at this expression here. This expression says how many chains in that volume is proportional to R, therefore proportional to N square root. So as the chain length change by a factor of 4, the number of chains will double. Chain length change by a factor of 9, the number of chains in the volume will triple, right? So that's why when you increase the chain length, there are more chains. So you keep increasing until this point. Until this point, according to this formula, it says, oh God, you're simply increasing the number of neighbors in my same volume. There is a magic number at which entanglement occurs because it's too crowded. For all flexible linear chains that we know in the world, that's the boldness of this assumption or conjecture. That it doesn't matter it's your styrene, polystyrene, or it's your polyethylene, or your PMMA, or your polycarbonate, or any of your polymer, or your polybutadiene, or your polyisoprene. It is suggested that no matter which of this polymer you have, entanglement occurs at a particular Q. E, let's call E stands for the onset of entanglement. Okay, so it's constant. Since you are probably very eager for me to tell you what this number is, I tell you it's on the order of 6. About 6 chains in my own volume. It's clouded. People say 3 is a company, but 3 is not enough. You need 6. But more powerfully, look at the formula of Q. Okay? Look at the formula of Q. It basically says, remember, R is a function of N. Therefore, R is a function of, it's an explicit function of N. It basically says, at the entanglement, when N equals NE, because of this expression, it says it is proportional to P. Because R over P by this conjecture is argued to be a constant. So, so this end-to-end distance for different chains is different. Well, I haven't told you enough except to give you that homework. Go ahead and figure out what P means. Remember one of the lectures earlier? And I don't know whether you further thought about what P is. Have you? After the class? What do you mean by aspect ratio? No, you don't need to go any further than the definition. The definition was, was that the physical volume is this. And it implies that if I have a pancake of diameter 2r, okay, that pancake has a thickness. I know I'm going to try to draw the third dimension here. Has the thickness of P. Or rather, this expression says that pancake precisely have a thickness of P. You know, aside from a pie, you know, but roughly speaking. So my offer for you about the meaning of P. Remember how I did it? Right? I just collapsed it. I just collapsed this open coil into a pancake, right? Next to each other, collapse them. And I find the thickness, and that thickness turned out to be P. Therefore, that P is reflecting the diameter of the chain, which I called molecular thickness. So if I tell you that styrene is very thick and polyethylene is very thin, you probably will not object to me. You probably will agree. And indeed, that's the case. So P is some kind of chain thickness. And different chains can be different, as I just said about styrene versus polyethylene. Okay. So there are a lot of connections to make here. So the conjecture that says Q at the onset of entanglement is constant, which is equivalent to say the end-to-end distance for different chains is such that if my P is larger, my end-to-end distance at the onset of entanglement is also longer. Yeah? By definition. Now, here the rest of what I have to say. I just indicated, in fact, we will have this all in the table. For example, polystyrene. Give you some impression now. Polystyrene, the P is about almost 4 angstroms. Okay? Polyethylene is something on the order of 1.7 angstroms. Okay? Which, of course, more than double. The styrene is more than double the ethylene. Which means my end-to-end distance for styrene will double, will be twice as long, more than twice as long. By definition. By this conjecture, if it's true. And I of course, promise to show you it is true by comparing with measurement. So, what else I should say? If styrene is twice as long, then I know I do this interchangeably. End-to-end distance is the same as radius duration. Then what this means? Well, R is that's R or G, doesn't matter which way, right? So what do we mean by styrene will need a bigger G, a bigger RE at this point? Well, it means two things. This is something that I have to give you a paper about, but it turns out polystyrene versus polyethylene, their Kuhn length is not that different. So therefore, for this R to be larger, it means there are more number of Kuhn lengths, or more number turns out to be repeated units. So it turns out that for styrene, you simply have to be longer to be clouded. This is not very difficult. Give a fixed volume. I have changed this thick, I have changed this thing. Same volume. If I put them in, of course, I can only feel less change if the change is thicker. And that's the styrene. And so the only way I can fit more is give me a bigger volume, right? And since I need to fix 6 chains in my volume to reach entanglement, styrene simply have to be longer. So this is all quite trivial. In fact, therefore, let me just rephrase it, expression we already had. Which is this, very crucial one. So let me try to see if I have all the steps for you. So in the packing model, the first concept is to introduce packing length. The second point of this model is this conjecture. What is conjecture? That this is constant, right? That's the conjecture. The third one, we can move on. The third is all just the consequence. Now we have finished. Introduced what is packing length, introduced the concept of the conjecture. The rest are just some further analysis of the consequence of this conjecture. So let's examine that consequence. If you go back to our expression, that this is the physical volume, it is P R squared. I'm just rewriting it. At onset of entanglement, in other words, when M is ME, R is RE, because you are that's the onset. We know at that point R further is known to be proportional to P. So I can write this the equation above again. ME rho Avogadro constant P RE squared. Essentially, it's P third power. Okay? This is a powerful relationship. The molecular weight for you necessary, lowest molecular weight for you to have the emergence of entanglement. Entanglement defined as how clouded it is in this model. That's perhaps was the word what packing means, how clouded it is. It's going to be proportional. It's going to be described by the molecular weight in terms of the packing length. Yeah. All the different polymers must find themselves in its own pervaded volume 6 chain. For a polymer that's very thick, the only way to fit 6 chains in my pervaded volume is a bigger volume. Huh? Yeah, that's the whole point. No, two long chains, if it's not space filling, you have to keep adding until it's space filling, right? Right. If you did, okay. How many chains you can fill is computed here. It keeps increasing when the chain length increases. So that was the whole concept. You start with chains that are so short that in its volume there are no 6 chains. There are only 3 chains. That's not going to be entangled. So you are going to keep increasing your chain length or molecular weight until you find in its own space there are 6 chains. And this 6 chains is a universal number for all different polymers. So by the time you have 6 chains, you will have entanglement. And the consequence of that is that that chain at entanglement length will have an end-to-end distance that's proportional to P. And here we are just translating that into something more concrete in the sense of at that entanglement, having 6 chains in itself, what would be the molecular weight for styrene, for polyethylene, for isoprene, for butadiene? You have this pervaded volume, which keep increasing as your chain length increases, right? So you just need to keep increasing your, until you meet the point where there are 6 chains in it, right? That's the point. That's the moment you reach entanglement for all polymers. That's the bold conjecture. I'm just translating that to asking, because you go to the lab, you don't use chain length, you use molecular weight, for example. So you're asking, gee, what is molecular weight of polystyrene for entanglement? Such that when I pick up this molecular weight, I find 6 chains in my own pervaded volume. And what is the molecular weight for polyethylene? When I pick that molecular weight, there will be 6 chains in myself, in my own pervaded volume. Yeah? Because that's a crucial concept. Because entanglement means at least ME. In fact, at least I indicate it should be at least 2 ME. And everything speaks relative to that. So when people say in polymers don't give you any excuse when people say my polymer is very well entangled. It immediately should translate for you that M over ME, which often in the literature called Z, is large. That's what it means, my polymer is well entangled. So you should never give you any excuse if you say, oh, I don't understand that language. No, you do. You better understand that language. That's exactly this point. So this is why ME is so crucial as a concept. Right? So I think I know it takes time for you to absorb this concept, but once you have, I was moving on to show you utilizing the conjecture which gives you this to show you that actually the entanglement molecular weight will scale with your P to the 3rd power. So you can do a very trivial mental exercise here already. Keep in mind, the density for different polymers are all the same. We're going to treat them as water atoms, right? 1,000 kilogram per meter cube. Avogadro constant is constant. This proportionality constant in front is the same. So really, ME is 3rd power of P. period. Really, right, by definition. And therefore, if I tell you Me is about 1,000 grams per mole for polyethylene, what would be the Me for polystyrene? You can figure out from here. Well, if I give you the tabulation of P, which I did. Right? 2 point something raised to the third power. So it's something on the order of 10, a little over 10. And now you should never be pretend you don't know that styrene has Me 10 times, more than 10 times that of polyethylene. Any questions? So let's explore a little more. Well, in fact, let me first show you, convince you
Hi, Dr. Wang, can you hear me?
That it's indeed true. So I will upload this paper, this first two figures from the book. The last figure was from a paper. I need to upload that paper to the Brightspace. And I'm just first going to convince you that that this is RE. And this is NE, or NE would be RE squared, of course, right? Because of Gaussian chain relationship. And therefore it should be P squared for all polymers. So look at these two graphs. For different polymers, indeed, remember that this being proportional to P is what the conjecture says. It's coming out of the conjecture. Remember here I argued. We have it on the recording if you have to eventually go back to it. So indeed, out of 50 different polymers, more than 50, it all collapses onto each other, onto this line. Double log with a slope of 1. And for this one, of course, slope is 2 because it's proportional to E squared. And moreover, this plot shows Me is indeed on double law scaling with P cube linearly, therefore Me is P cube. I'll talk about S later today. So basically you see that it turns out there are 4 independent groups at about the same times of mid-80s who proposed this concept of the conjecture, arcing length conjecture. And it turns out our polymers, most of the linear flexible polymer that we are familiar with, known, commercialized or not, many of them are what we use every day, indeed obey this relationship. Yeah. Okay. It's a good question. It's a question, actually, it was addressed from the beginning. Let me just address that to you. Here. Let me write that physical volume on the other side. It's m rho value constant. Okay? So her question was, let me just rewrite it so that I don't mess up this. Her question was, let me write it at onset. Her question was, how come ME goes with P to the third power, or NE goes with P to the second power? If you claim NE is proportional to ME. Well, two things I can say. When I say proportional, what's constant in this proportionality involves P. In other words, I'm only concerned myself with doubling my chain length, whether molecular weight doubles. Of course it doubles. But more trivially, it's exactly what I argued here. That I said your physical volume, which of course is directly proportional to the molecular weight, should be linear in chain length by definition. But remember, there was an extra P that has to come in because otherwise my dimension is not the same. So that's why the extra P comes. Right? Yeah, so that's how it counts. Good point, though. Sometimes I even look at this as, gee, God, how come NE is only squared, not cubed? So, yeah, quite trivial, actually. Since we are on this page, you may as well wonder, how did they measure it? So on one side, for example, how do you determine ME? In principle, let me just try to tease you a little bit. In other words, to give you a sense of what's going on. In principle, if I take this relationship, okay, I can say, oh, I know how to determine ME. I can just determine what is MC, right? Okay? For all different polymers. I tell you, that's a very laborious job. Why? Because for you to do that, is for you to find all different molecular weight, fill up this whole curve, and find where the kink is, right? And you determine that for one polymer. And then you move on to the other 100. 100 times, let's say, 10 points, at least that's 1,000 experiments to do. But there's a more direct way that for each polymer, you only need one sample to do it. So let me show you that. Yeah. So the argument there goes back to viscoelasticity, goes back to rheology, goes back to what we have talked about. Which is what? Which is, I'm going to claim for you that the oscillator shear measurement will allow you to do that. In particular, there's a plateau modulus that's called GPL, plateau modulus. So we're going to figure out if you can measure plateau modulus, then you are in business. But plateau modulus, we did more than once when we discussed viscoelasticity. It has the dimension of energy per unit volume, so the energy is kT. The volume is the number of chains per unit volume. Well, until you think a little further, what my language may need to be revised. Remember, modulus is a measure of stiffness. And you learn from rubber elasticity, the stiffness depends on how densely cross-linked you are. So we are talking about ME again. In other words, the G for a melt, this PDMS, it has a particular level of modulus, that give you a sense of elasticity. The level of elasticity in terms of stiffness is reflected in G. Is reflected in what is ME for this PDMS. Is reflected in, therefore, the value of G here. And therefore, I need to do a slight modification. Oh, gosh. That this is not the number of chains, but the number of such, what do you call it? There's a word you may use. You can call it entanglement strand. You can call this whole thing mesh size. Meshes, in fact. Entanglement meshes. Or if you like, meshes of the entanglement network. So how many such strands per unit volume? Well, it's exactly this many, right? Again, you know the molecular weight of each strand, you know the density, so this is the molar number of strands per unit volume. Each mole has Avogadro number of it, times kT. And this is classically written as rho R. Let me have a little italic R. We're running out of symbols. This R is gas constant. And if you have seen this formula for the first time, fine. But try to remember it because this is a very useful formula saying that G is 1 over ME. And this is how folks determines ME. By reasoning that this is how it involves in the plateau modulus. So you make an oscillator shear measurement to determine the plateau modulus and use this value to evaluate, because you know the density of your polymer, you know Avogadro constants, you know at what temperature you made this measurement. You precisely know what is ME. And we have a tabulation of this value for all known polymers. They are, of course, equivalent to P, so the formula basically says G is also 1 over P to the third power. This is powerful. This is very powerful because you are going beyond a structural concept into a mechanical concept. You are basically saying, gee, if the P is smaller, my untangled melt is stiffer. This value is higher. By a lot, because it changes to the third power. As I said, it's true. So now comes back to how you measure it. If you measure the stiffness and you find indeed it's changing with the P this way, such that it goes with 1 over P third power. Any questions on this? So all this is described in the book. Just want to show you the pages where this occurred. Basically, it was on page 35 when we discussed the packing model. And if anything, I was trying to be convenient and connect with you, connect for you in terms of symbols, is that I have been keep using R here. In the book, we call this L. And T stands for entanglement. And distance for a chain that is of the length of N. So that's just that's the symbol that's going to be let's keep making sure we have the same symbols. So with all that, for example, this formula is 2.30 B. That G is 1/3, 1 over P third power. Okay. Is it clear? Okay, so now it's for you. Perhaps it's no longer so abstract. Actually, we know how through the viscoelasticity we learned how to measure this ME. And as I said, there will be a literature I will upload that tabulates for all polymers what is ME, what is P for each polymer. Therefore, very useful for you. Now, moving on, there are yet a few more things to expand, to say about. One is this idea of so let me call it 4. We're going to talk about areal density. So I think the best place to start is this place, that it's just another way to formulate it. G, this plateau modulus, is the number of chains, number of entanglement strands per unit volume. In other words, the number of strands per unit volume is, of course, simply just 1 over the physical volume of an entanglement strand. And that is nothing but KT, according to the definition of packing length, and entanglement length squared. Right? I want you to draw an analogy of that so that you're not confused with what we started here, this expression. Right? The physical volume is related to its end-to-end distance of a Gaussian chain by P, and I'm repeating the same for this little Gaussian chain, which is a strand, which is a strand here, and that's this. Right? So I'm going to play a little magic now. I split this into 2 terms. And if you recall, we had briefly introduced this. The first one is what we called some kind of elemental elastic force associated with this strand being kept at distance. And if you recall, the other formula, the other quantity is an area density, such that our modulus is written as if we're dealing with stress, which is how many chains per unit area, each chain contributing how much force. Yeah? And by identification, we're saying that this area density is 1 over P entanglement length. How come? The question is how come? Is it the number of strands per unit area? Meaning, you basically, you're going to treat this as I once told you, treat this as how many chains are coming out of the board per unit volume, or per unit area. So the way to roughly figure out this is rather straightforward, is going back to the original definition. You have a coil that's reaching the level of entanglement, and in that same space, there are many other chains. Right? I told you it's a 6, but who cares? It's a single number for all different polymers. So you are going to imagine cut through this volume, just section it. Right? If you section it, you're asking yourself how many chains are coming across this section. Well, that's very easy to figure out. Lord. How many chains are coming out? Well, how many chains are in this volume? QE of them. Across an area, how much? Well, it's pi entanglement squared. Right? Treat it as just a circle or sphere, cut it from the middle equator. Right? Roughly speaking, it must be true. So if I go back to what is QE, QE is entanglement length over P. I know we had a slightly different notation before. That's okay. Let's see where we are. Here. Q is there. I'm going to change my molecular weight until it is QE. So I have QE on this side. I have RE, which is less L. So basically, I have QE being that, being this. And the bottom, if I ignore the pi squared, the pi here, it's a square. One of this canceled. And that's that. So it's not so frightening to find out things like this. Right? Because it's just go by definitions here. You have however number of chains, in fact about 6 of them. In its own volume there are 6 chains. I'm going to cut it through over my own diameter. I'm not going to cut 6 chains, of course. So if you like to do one more step, it is to recognize that this area density is in fact goes with 1p squared because entanglement length is proportional to p. So in that sense, I can make an argument, oh, this quantity, which is nothing but this, is simply, because QE is a universal constant, it is simply 1 over squared. And that is, of course, proportional to p, therefore it's p squared. So I'm going back to this. So in any case, I have recovered an expression, which is equation 2330C, which we have seen it previously in chapter 1. Let me just give you. And that's where, that's why this expression here inspired us to write that expression here for rubber elasticity. Remember, I was talking about an alternative way to think about what is modulus G in your rubber elasticity discussion. It's no longer abstract. It is actually a force times the area density. Any questions? As I said, the good thing is if we have this recorded, you have a chance to digest it by going it one more time. If we are, I think it is allow for you to immediately digest. So my goal here was for you to just hear the logic, the fact it makes sense, and the deeper meanings is for everyone to chew on it and to. But I tried as much as I could to indicate for example, the meaning of P, very essential. Okay, so any questions before I move on? So to me, this is quite elegant that we have. In fact, this notation, I think, is original, meaning I'm the one proposing to look at it this way. I don't think it exists. Well, it exists in my book, but not prior to it. It really dissects what's going on when you move further to see where how this entanglement participate in giving you viscoelasticity. And the G, of course, is the elastic part. It is associated with the chain. See, because this concept here is nothing but rubber elasticity that you had. That when you hold a chain to a distance, you find you need a force of this level to hold it. If you don't allow it to sample its own space, this constraint is what the chain doesn't like, and they resist that constraint by giving you this force. That's the classical notion of rubber elasticity. I know we, in the outline, we're supposed to talk about a case where this entropic elasticity concept, that you are limiting the number of configurations it can sample. Because, right, if the chain ends are free, there are many more they can assemble. They can find themselves to be in at different times. But now you're just holding them there, you're limiting the amount of entropy there is. And that's not favorable, so you pay a price, right, by having to have a force there. What we omitted a great deal is when this chain becomes highly stretched. So high that this entropic force is not going to account for it. So high that there will be energy involved. In other words, the bond will start to become stretched to some degree, and there is energy involved, enthalpic energy involved. So that was a part, even if I discuss, it will be somewhat casual and loose because it's not formally presented in the book, for example. So I will not go further on that, except to remind you here, we're talking about entropic force, which whose validity actually is limited when we try to, for example, stretch this polymer very, very fast. Because the internal time scale of this PDMS is so fast, I can never stretch this fast enough. I want to keep emphasizing whether you can stretch fast enough is this time to make a significant deformation. For this, I can never get this very large enough, let's say 1,000. I cannot do that. And therefore, I am only going to be in the limit where the force I experience is elastic, not enthalpic. Elastic, therefore entropic. Okay. All right, let's move on. I have a few more minutes. Let's move on and move to the next model. And before I do that, there will be just some additional concept to be introduced. So first thing first, we are talking about packing models. So I realize I didn't give you the title except at the beginning. There is the packing model as the section 2 of chapter 2. Number 3 is about different entanglement models. So the first one is packing model, and the second one is the so-called, what I'm going to go through, the so-called percolate. Oh gosh. So-called the percolation model. Okay, so we will talk about a little bit about percolation model. This was a different attempt by a particular person. Very unfortunately, he passed away a few years ago. Probably a heart attack or something, just all sounded unfortunate. So he was also trying to answer the question, what is this critical molecular weight for entanglement? But he had a different idea. And this idea might be useful when you have large deformation. So that's why I mentioned it here. It turns out it's not useful for figuring out what is ME, if you think ME is related to the plateau modulus like this, then this model doesn't work. But the concept that's in there is important. So I will discuss this first by introducing a slightly related concept. So if you treat your chain as if it's a little rod, then of course you can think of this as a cross-section S. And I claim that this cross-section is proportional to P because I convinced myself P is describing how thick this chain is. So let's see how we can do that. We know if you have a chain, the physical volume is P R squared. And they are really let's do it. So if you think of your chain, break off your chain to each monomers. Each monomer has a bond length of L. And how many monomers? You have an L number of monomers. Because they are, N, let's say N is the number of repeated units. In a chain. Okay. Then geometrically, I can tell that S times the chain length is my physical volume. Right? Just treat this as a rope that has certain cross-section and certain length. Then my physical volume, of course, is length times the cross-section of the rope. So, so this basically allows me to write like this, and the chain length can be written either in terms of repeat unit or in terms of number of Kuhn lengths. So you can see now, by identification, this is this. In other words, S is P times Kuhn length. So as promised, your S indeed is proportional to P. And this is expression 2.38a in the book. Any questions? So this is just a little section for me to further illustrate for you why I claim that this P represents the thickness of the chain. Because it is the thickness of the chain in the sense of cross-section as S is proportional to P. Of course, when we say that, it's rather convenient to treat this Kuhn length as the same for all polymers. And that's how you can say that the cross-section changes just as P changes from one polymer to another. So I know I'm going to run out of time, cannot finish the rest of the discussion. So we'll come back next time. I have to find when the room is available if we need to make it up. But basically, we'll come back next time to have another way to think about entanglement. In fact, the way Richard Wu was thinking about entanglement was, this part is quite amazing, actually. Keep in mind, so I know we talked about entanglement. We talked about the consequence of entanglement, the elastic recovery, the plateau, and so on and so forth. I hope you still remember now. It's all listed in the book. We speak of entanglement quite formally starting recently, without exploring all its viscoelastic consequences. But we start to talk about structural meaning of entanglement. And you have seen some so far, okay? You have seen some so far according to the packing model. It recognizes that the topological, if not, just the packing aspect of it, that if there are too many chains around myself, then that's entanglement. Nothing very specific. It's just how clouded it is, right? That's entanglement. But Richard Wu had a different idea, which I really like, and he has some sense in it, which is something not, from a conceptual viewpoint, is not new. What he has, people have had this notion. Forgive me if I cannot trace back who had this notion first, but we should be able to find it later. What he has in mind is, this is entanglement. And this arises merely from the fact the chains cannot cross. It cannot cross. Unless you break the chain, but we're not in that limit. Right? So not only that, of course, you have, sorry. Let's start mismatch again. You have the next one. And keep going. Right? That's another way to think about entanglement and the network of it. It's because when they are so long, they cannot avoid it, but inserting each other and not constraining each other. And you see, so this chain goes on here. You see, this form of network would not be there. Watch. It will not be there if it's not long enough. How long it need to be? Well, how long it need to be? Well, it look like what I draw there. Is about barely enough, long enough. Yeah? This is about barely enough. Agree or not? That this is sort of a minimum you need to be in length to exploit the possibility of uncrossability. Keep in mind, you have to be lucky that they are uncrossed. You can fold a few times without other chains in that place without this red chain and another, this thing doesn't change color as easy as I can do there are two of them. So what does this mean? Oh gosh. You see that it's not calibrated, so oh gosh. So I was just merely trying to. So they are basically going to cross. If you treat this as a plane, sorry, God. If you treat this as, I didn't draw it. Basically, you treat this as a plane and cut it. You're cutting this chain in 3 places. Yeah? And if the chain is shorter, if the chain is shorter, you're going to cut it only twice. And if it's twice, probably that's not going to give me entanglement. Okay? So when we come back, we'll figure out how to account how long the chain need to be to cut it 3 times. Okay, any questions? I don't run out. Any questions? All right, we're done.